All right, so this is the second of the three steps. This would be transduction, and I'll have to say this will be probably the shortest of the videos, but it also is probably the more complicated. What we're going to do is kind of go more of an overview of what's happening. I don't obviously want you to know all of the little steps on these. Again, this is more a kind of a cell molecular course should be doing, but I want you to kind of get a idea of why this happens. And really what it comes down to, especially with this first one, is it is control. So here we have a signal transduction pathway. So this is a protein phosphorylation cascade. Phosphorylation is really kind of a simple way of, it's a complicated way of saying adding a phosphate. So you can see we have ATP here and we have these steps, and the ATPs are all adding a phosphate to these kinases and these reactions. Okay, so what we're doing is we're activating this cascade. So we're going from one step to another, to another, to another, and eventually getting to our cellular response, which we'll talk about on the next group. By having a cascade like this, it can do multiple things. And we're going to look at that with responses, increased responses. But more importantly, it does give you more control. And there are lots of different parts of this pathway that you can change to give you a little more fine tuning. So again, a protein phosphorylation cascade where you have all these protein kinases. And what they're doing is just adding a phosphate, and one step sets off the next step, sets off the next step. All right. The second one are using what we call second messengers or secondary messengers. And the second messenger is not a hormone, it's something a lot bit smaller. And the best example, or one of the more common examples, or actually the first example found, I suppose, was CAMP, cyclic adenosine monophosphate. And so this little tiny molecule, you can see here's one of our receptors, the G protein coupled receptor we talked about earlier, that gets set up, and then that messenger, actually the message gets sent, and what happens is CAMP picks it up and takes it into the cell. Intracellular means into the cell. The advantage of having something this small is it can actually diffuse very quickly, so that message can go in quickly. It also can be taken out very quickly. So it's a way to close that down and inhibit that response very quickly. Also, and we'll see this with responses, depending on where it goes and what it hooks to, it can have multiple effects. And so this is a quick and easy way to send messages throughout the cell that a hormone or a bigger molecule may take more time to do and may be a lot more difficult. All right, and then the third one is a little more complicated, and again, we don't want to go into all the different things here, but we're looking at inositol trisphosphate, IP3 is how I want you to remember it, because I'm not sure I can spell all that. But IP3 is a secondary messenger. Here we have kind of the same thing going on with our G protein coupled receptor. And then what happens is we have some transitions, and I don't care that you know those transitions, but what you end up with is this IP3 messenger, which then goes across and may activate things. But usually what it does is it actually hooks onto a calcium ion receptor here. We have this ion ligand channeled ion. And so what happens is the secondary messenger here acts as the ligand to open up the calcium receptor and allow calcium through. And then calcium can also act as a secondary messenger. And again, what's great about this is it offers lots of control and lots of speed. So that's what you're seeing here. So I want you to keep that in mind when we talk about transduction, and the reason for these secondary messengers and the reason for these transduction pathways is really control and speed. All right, with that, I think we'll go ahead and stop the recording.